At offset 12 within the value data, there's a 4-byte value, and it is the size of the graphic. So when you interpret that data, the 4-byte value, it will give you the logical size of the graphic itself in bytes. And then at offset 16 is the beginning of the actual data itself for the graphic, and it will typically end in a signature at the end of the file itself that gives you the BMP signature format. And then you'll also see at the end of that is the volume letter, the full path, and the file name for the user tile for that particular account. In other words, where the graphic actually originated from. Okay, user account control was introduced in Windows Vista, and it continues to be prevalent in Windows 10. So disregard what you see there on the slide in that first bullet. It is a security component that enables users to perform common tasks as non-administrators, called standard users, without having to switch to an administrative role or a user account. Limited user has no administrative rights and cannot install software or perform other administrative functions without the permission of the administrator. So if a limited user opts to install software, the administrator's password, standard or administrator, is required. And UAC is enabled by default, but of course users can manipulate this in Windows Vista, Windows 8, Windows 10, Windows 7, and so forth. So to determine if UAC is currently turned on or off, you can navigate to the Software Hive and the Microsoft Windows Current Version Policies System subkey and locate the Enable LUA value. And you can see that UAC is turned on if the value is 1, which it is turned on by default. And of course, if it's turned off, you will find a value of 0. Sometimes a very overlooked subkey in any type of Windows investigation is the Software Microsoft Windows NT Current Version subkey, which contains some very basic information, although very important and relevant in an investigation. And that is the installation date of Windows itself. It is stored as a Unix date and time, a 32-bit value. Also is the product name, which is stored in Unicode, basically the name of Windows. So it could be Windows 7 Ultimate, Windows 8 Enterprise, Windows 10 Enterprise, whatever the naming convention happens to be for that version of Windows. Also overlooked sometimes is the registered owner and registered organization, both stored in Unicode. This is a very important area to examine because the value that's in here, especially when you're trying to tie it to a specific user or an organization, is certainly relevant to any jury or any type of judiciary that's evaluating the evidence at hand. The next area we're going to look at is the user assist subkeys, and this is stored in the ntuser.dat file. And the user assist subkeys tracks any type of local program, application, or file activity per user. And this is definitely a area that you want to examine in good detail when you're looking to find any type of artifacts related to user activity, program installation activity, things of that nature. At least in the enterprise version of Windows 10, user assist keys track user activity much like a running log file. In the example screenshot that you see below, there are a series of GUIDs, globally unique identifier subkeys, followed by a subkey under that, which is count, and we'll explore that here momentarily. The screenshot on the right looks like a bunch of encrypted data, which to an extent it is. And the reason for that is because the data in those subkeys, meaning the values themselves, are actually stored in ROT13 encryption or ROT13 encoding, which is Caesarean cipher or rotate by 13 places. So an example of that would be the letter A would be listed as N while E would be listed as R. And so the data looks like what you see below. The two subkeys that are of special note for examiners, and this is consistent in Windows 7 and Windows 8, are the GUIDs that begin with CEBFF5CD and F4E57C4B. The first one being the location where you'll find the presence of files that were executed on the volume and by that user, and the second being shortcut file execution. So you'll find the combination of those in those count subkeys. As we look inside the subkeys below, you'll see the GUID that's in a globally unique identifier contains the count subkey. When we look at the registry viewer, it automatically decrypts the ROT13 encryption, and it shows you the content over in the key properties. So for this one that's shown over here in the right pane, you see the P:, HF, REF, etc., and it is being decoded by Access Data's registry viewer, and you can see the value name in ROT13 is C users read downloads ace money light setup.exe, and that occurred on December 4th, 2014 at 2049 hours in UTC. And it also shows you the number of times that that was actually executed. In this next example, we see that the user executed Regedit on 6 different occasions. And of course, the last written time for the subkey is irrelevant, meaning the key properties that you see up here. However, we see that the last time that this value was updated, which is actually stored in the value data, was on December 5th, 2014 at 0002 hours or 0002 hours and 52 seconds UTC, which is actually December 4th, 2014 at 7:02:52 p.m. Eastern Standard Time, or 1902 hours. And of course that is accurate based on the validation and testing that I have conducted. When you look inside of the value data itself in hexadecimal, you'll also see the correlation between the file time value that's stored, again encrypted in ROT13, but when decoded you see the file time value is 600538D01E10D001. And when that value is decoded in the decode application, we can see that that time validates to a T. And of course I have applied in this screenshot here an offset of 5 hours from UTC, which is consistent with what the application is showing me. In this next example, we see that the user executed a program called setup64.exe from the D volume on 1 occasion. And of course you see the last written time for the subkey is mainly irrelevant, but you can also see the time for the user assist entry is certainly relevant to this particular instance if this is something that is important to your case. In a network investigation, it's sometimes important to determine the name of the computer as it appears on a network based on the evidence that you may find in other artifacts throughout the Windows operating system or even other operating systems that may be on that network. The computer name itself is stored in a value called computer name in the path that you see on the screen, which is stored in the system hive. And sometimes this computer name is sometimes referred to as the NetBIOS name, and this value is stored in Unicode. Windows services are stored in the system hive in the control set, typically 001, and then the service subkey, and the subkeys that appear beneath that are the services that are available to run on the local machine. When we look inside of the particular service, for example, in this screenshot is defrag service. It is currently has a start value of 3, and this means that the defrag service can only be run manually. But there are other services on this local machine that will start automatically or in some instances be disabled. And the values that you see up on the screen from 0 to 4 are some that you may find in an investigation. Okay, so the DHCP the address itself is stored in the system hive in the path that you see on the screen. And when you navigate to the DHCP address value, you'll see that this is the DHCP IP address that was given to the computer by the server or the router or the service. Sometimes in an investigation, the legal notice and the text that appear on the screen when a user logs in may be important to your investigation. If it is, then this information is stored in the software hive in the Microsoft Windows current version policies and system subkey, and there are 2 values, legal notice text and legal notice caption. And this information will be displayed when the computer goes through its normal boot up process. And before a user can log in, this information is displayed on the screen. In this case here, you see that there's warning, 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 and the content of this system is encrypted with Windows, etc., etc. If you believe that someone may have been manipulating the registry in any way, or trying to put any information in to the registry, create new values and subkeys, this information is stored in the ntuser.dat file in the software Microsoft Windows current version, applets, Regedit, and then last key value. And you can see that the information here shows us where the user last viewed the registry. And the only way that this gets updated is when the Regedit application is running and the user cleanly exits the Regedit application. And this is of course specific to each user account on the local machine, hence the presence of the ntuser.dat as you would surmise. Another area in the registry is the area where the ability to show or hide files within the operating system is enabled or disabled. I'll give you an example. In a high-profile sex crimes case many years ago, the user took photographs of the victim and right-clicked over the top of all those files and applied the hidden attribute and went into the registry to toggle that feature on and off, and we were able to show that through the restore points at the time on Windows XP on that particular machine, that the user was toggling on and off the hidden show hidden files or do not show hidden files attribute. So if files are hidden, that may not necessarily be a defense, meaning if the hidden attribute is applied to a file. If the user is able to view those hidden files and you're able to show that they were able to do it. In some cases you can certainly show that by navigating to the ntuser.dat and looking at this particular value. Conversely, you also have the option in folder options to show or hide file extensions. And as you'll see up on the screen, it's basically the same type of path in the ntuser.dat, except that you'll locate the hide file extension, hide file ext value. And of course you see the value data will either be a 1 or a 2 for show hidden files or do not show hidden files. In a forensic examination, it's certainly possible that you may want to show whether a user had the capability of looking at files that have a hidden attribute on the volume, or even folders that have a hidden attribute. As an example, it worked on a sex crimes case many years ago where the user took photographs of the victim in explicit situations and applied the hidden attribute to those files and the parent folder, and toggled the show hidden files on and off through the folder options in Windows to reveal the content of those graphics. And we were able to show through this registry setting that the user was in fact able to view the hidden files on that local machine, even though that the defense was, well, I'm not able to view the hidden files because they're hidden. They have a hidden attribute, therefore they don't appear and they're not accessible, when in fact the user had it set up that they could in fact look at the files that had the hidden attribute. So what we see in this screen here is that the hide file text value, if the value is 0, it will show the file extensions, and if it, in this case here, it has a value of 1, it will not show the file extension. And when we talk about the hidden files, we're able to also look at the similar location, the same path but a different value here of hidden, where we're able to determine if the user could look at the hidden files. If the value is 0, then it will not show the hidden files, and if the value is 1, then it will show the hidden files. When we look at the most recently open files, we can find this information in the ntuser.dat hive, and specifically for applications and files. If you navigate to the Software Microsoft Windows Current Version Explorer ComDLG 32, which is ComDialog 32, there's a series of subkeys. Two of note is last visited PID MRU, and also the open save PID MRU files. One's for applications, one's for files. Applications are generally listed, but this is based on the developer, including the registry data itself. So a developer has to write the program so that these artifacts appear, which most of the Windows authorized or signed applications, approved applications, will utilize this registry subkey. Inside of this subkey itself, the value, a 0 value name is most recently open file. 1 value name is just prior, and a 2 is just prior to that, and so on. So we take a look at the file that we see up here on the screen in the open save PID MRU. A file named me.jpg is the most recently opened file by the user, and this is of course viewed in NCase version 7. And the 0 is the most recent, and 1 being the next one that follows that. If you look in the last visited PID LMRU, the most recently open application is iExplorer.exe or Internet Explorer. And we see that in the screenshot within NCase as well. Previously in this lesson, we looked at the typed URLs that were typed into the Internet Explorer browser by the user, and that information is stored in the ntuser.dat and the Software Microsoft Internet Explorer and typed URLs subkey. And when we look inside this subkey, you'll see that URL 1 is the most recently opened URL or typed in URL by the user. URL 2 is next, followed by URL 3, and so forth. So it's kind of a garbage in, garbage out type of scenario. And don't forget that we also looked at the typed URLs time subkey as well, and we found the file time values that correlate to the URLs that are in the typed URLs subkey. When we seek to obtain the artifacts and settings for Internet Explorer, we can navigate to the ntuser.dat hive file and navigate to Software Microsoft Internet Explorer and main. And we'll find the browser settings such as the start pages, the secondary start pages, and things of that nature that are stored inside of this particular subkey. Here you find that the start page is listed as ucf.edu, And down in the secondary start pages, you see the DaytonaState.edu and FSU.edu, all Florida colleges. So as you may recall, in Windows Vista, Windows 7, Windows 8, and Windows 10, they no longer record the last access date and time in the standard information attribute of each MFT record. In other words, last access date is basically turned off by default, but a user can turn this on. The value itself is stored in the system hive, and the name of the value, as you'll see on the screen there, is NTFS disabled last access. Now 1 means that it's not updated, and 0 means that it is being updated. When you go into the registry subkey itself for the file system, you'll see the screenshot at the bottom portion of the screen, and you'll see that the value is currently set to 1. So this concludes the portion of the lesson on Windows 10 artifacts. These are some of the most common artifacts that you'll want to examine in just about any type of forensic investigation or examination. Surely it is not comprehensive. There are many other artifacts that we could spend hours and hours going over, literally going through each level of the registry to explain it further. But the intent of this lesson is to give you an overview on basic navigation, basic structure, terminology, and some of the most common artifacts that you'll find in the Windows registry. Next, we're going to talk about the physical registry hive file and give you an overview of its structure so that you at least have some basic knowledge on how the registry is structured and how you'd be able to recover data should you get any type of a keyword hit or find any data in a manual investigation or a manual examination of a registry hive. So we're going to look at a couple of basic aspects of the binary registry. Again, it's not intended to be a comprehensive lesson on the physical structure of the registry because it's very complex. Just basic familiarization with the structure and can allow you to have this knowledge. So the big question is why? Well, how many times have you run across a search hit in Slack or unallocated or just by other examination techniques, and have you looked at something that might be relevant but not really able to look at the data structure itself and recognize its significance to an investigation or any type of case that you're working on? So sometimes you may miss critical data, and we certainly don't want you to do that. A little bit of knowledge will certainly help you advance in this area of Windows examinations. So some of the binary structures of the hive. We look at the binary structure of the registry hive, and it's composed of blocks and bins and cells. Blocks are 4,096 bytes in length, and the header of the registry has a signature of regf, or the hex value that you see on the screen. The first block contains information about the registry hive itself. So I'm going to bring up an example here inside of NCase, and we're looking inside of a users directory at the ntuser.dat file. And if we look in plain text for this file, we can see the path to the ntuser.dat is plainly displayed in Unicode inside the registry hive itself. We see C users read ntuser.dat, and that's the username on the local machine. Here is the header for the registry hive itself, which is consistent with registry hive headers. When we go into hexadecimal, and I navigate into a total of 12 bytes, the next 12 bytes after that, or excuse me, the next 8 bytes after that is a file time value. And this file time value is actually the last time that this registry hive was updated. Now inside of NCase, I can go to the date and time value here to decode that value, and it shows me the value of 9/13/14 at 2:33 a.m. And this way I'm able to go in and determine exactly when this particular hive was last updated. Again, in an example on the screen here, we see the offset of 12 from the beginning of the registry hive itself, and we find the file time value of 8 bytes, and we can of course decode that. And this is just another example so that you have this documented in your screen. Okay, looking at the physical content of the hive file itself, we see a view from a previous EnCase screen which has hexadecimal values on the left side and then plain text over on the right. Here we're looking at a signature of HBin, which is the bin area at the beginning of the block within the hive file itself. And when we look at that data, we can see the signature of HBin, which indicates that is the beginning of the bin itself. Immediately after that, we find a 4-byte value that tells us the size of the bin itself. And when you calculate that 4-byte value, you translate that from hexadecimal to decimal, meaning 0010 0000, and that gives you a decimal value of 4096 bytes. The very first entry that we find inside of this bin happens to correlate to a subkey. So in this entry here, you'll see that the very first entry, it occurs at offset 32, and the value that we find is FFFFFE0, which is a negative value for negative 32, and this is the size of the segment itself. If the value is negative, and it is, then the segment itself is in an allocated state, meaning it will appear inside the registry. However, if this 4-byte value is a positive value, then it's in a deleted state. Here we take a look at the next 2 bytes that follow that 4-byte value, and we find the signature of a key value, which is VK, or KV, in Little Endian. Now if we take a look at this example here, prior to the signature of the segment, we find the 4-byte value, and of course if we were to convert this value to decimal, we'll find that it's a negative value for this key name. And in the screenshot below that, you'll see the value is changed to 60000000 for the exact same key name. And in this example here, we see that the actual value in the registry has been deleted. We take this a step further. We take this value of FFFFFA0, and we see that we have a resulting decimal value of negative 96. And we see the value of 60 hex down here. And when we convert that to decimal, we get a value of positive 96, which means it's in a deleted state. So a logical view of the typed URL subkey shows us what this looks like inside of the registry editor. And a physical view of the subkey tells us that this is a subkey value, and we see the KN signature, and we see the file time, date and time, and we also see the subkey name in Unicode, which is typed URLs. Here we have a logical view of the typed URL value, and the physical view of the value itself is shown in the screen. Here we have the unique signature of KV, which is in Little Endian, and we see the value name of URL1 in ASCII, and of course the value data itself is ucf.edu. That's stored in Unicode inside of the registry. So now that you've been provided with a basic overview of the registry coupled with Windows 10 artifacts and also a brief overview of the physical structure of the registry itself, it's time to delve into a practical exercise. So some of the rules for this practical is you can use any tool of your choice as long as you validate your findings. I would highly recommend that you use a tool that is forensically sound, such as Access Data's Registry Viewer, and you can download that and use it in the demo mode for the scope of this practical exercise. Please note that in the practical itself, all of the date and time values that you list in your answers must be listed in UTC or GMT. In other words, an offset of 0 hours from GMT. Now, when applicable, you need to make sure that you list the name of the hive file that you obtained your evidence from, the fully qualified path, the subkeys, the value name, and the value data. And of course, to reiterate, the name of the hive file is very important. If you are listing a ntuser.dat file, you must list the name of the user, in other words, the user account that you retrieve this information from. This concludes the lesson on the Windows 10 registry. I hope that you found this useful and encourage you to continue researching the registry in Windows 10 and related operating systems. And I know that the value of the registry will certainly help you in your future endeavors in cyber forensics and digital forensics. Thank you.